Hello students, in this video I'm going to take isomerism topic, isomerism in carbohydrates especially. So I will make isomerism quite easy for you because in books the way this topic is given it is very confusing. So I'll try to clear all your doubts here only. Isomerism, I already told you in the previous video that isomerism is of two types. When any compound has asymmetric carbon, it will show both optical and structural isomerism. So the first type is structural isomerism. Structural isomerism, also known as stereoisomerism, which is further of four types, that is functional isomerism, enantiomerism, epimerism, enomerism. See again, it is functional, enantio, epi, eno, right? So let's get started. What is isomer? Tell me, what is the molecular formula for glucose? The molecular formula for glucose is C6H12O6. For glucose, it is C6H12O6. But for fructose also, it is same. C6H12O6. For mannose also, it is same. For galactose also, it is same. So, it is same molecular formula. But then what thing is different in all these compounds? That is, they all have something different in their structure. So, this is the definition that a compound having same molecular formula but different structure is known as isomer, right? So now we'll be doing the types. In the types, there's no need to mention what thing is same, because be it any type of isomerism, same will be molecular formula, and every time we have to see what thing is different. For example, now when we are going to start with the first type, that is functional isomerism. Functional isomerism. In this, now what thing is different? Same is, there's no need to mention what is same. Same is always molecular formula. Now what thing is different? In functional isomerism, there is different functional group. The functional groups of carbohydrates are aldehyde and keto. Do not take alcohol as functional group in carbohydrates. Either aldehyde or keto is the functional group, right? So when we say functional isomerism, then they have different functional group. One is having aldehyde, other is having keto, right? So let's see the example of a 3-carbon aldehyde and a 3-carbon keto. 3-carbon aldehyde, 3-carbon keto. Now I'm going to make the structure of carbohydrate. It is very easy to make structure of carbohydrate if you follow the sequence which I'm going to give you. That first make the carbon skeleton. Now on the carbon skeleton, first make functional group, then terminal carbon, then the remaining carbons. So I'll teach you how. First I have made the carbon skeleton from 1 to 3. Now first on this carbon skeleton, I will be making functional group, that is aldehyde group, which is present at C1. So CHO group is functional group here. Then I will make the terminal carbon, which is C3 here, because terminal carbon is always CH2OH, right? So that is done. Now after doing this much, whatever carbons are remaining, on all those carbons make H on left hand side and OH on right hand side. This is the structure of 3-carbon aldehyde. Now I'm going to make the structure of 3-carbon keto. So again on this carbon skeleton, the first thing we will make is functional group, which is now keto group present at C2. That is this, right? Now we'll be making terminal carbon. That is C3, which is CH2OH, but C1 is also terminal in this case. That is also CH2OH, right? So the structures are complete. Let's see the names. The name of 3-carbon aldehyde is glyceraldehyde. The name of 3-carbon keto is dihydroxyacetone. Short form DHA. So can I say glyceraldehyde and DHA are functional isomers of each other, right? Because they differ in the functional group, they have same molecular formula. Now see the names again, glyceraldehyde and dihydroxyacetone, because names are giving information about the structure. When I say glyceraldehyde, see it is aldehyde written in the name because it has aldehyde group. Then the other name dihydroxyacetone. Why the name dihydroxy? Because it has 2 hydroxy group in both the terminals. That's why, right? Now let's see the structure of 6-carbon aldehyde and 6-carbon keto. 6-carbon aldehyde is glucose, 6-carbon keto is fructose. So let's see how to make the structure. 6-carbon aldehyde is glucose, 6-carbon keto is fructose. Both are functional isomers of each other. first make the carbon skeleton from 1 to 6. Then on this carbon skeleton, first we will make the functional group, that is C double bond O at number 1 position, completing the valency with hydrogen here. So aldehyde group at C1. Then C6 is CH2OH terminal carbon. Now on all the remaining carbons, we will make H on left hand side, OH on right hand side. So here like this, like this, like this. But at C3 you have to learn that it is H on right hand side, OH on left hand side. This is the structure of glucose, right? Now let's make the structure of fructose also. Again, first is carbon skeleton from 1 to 6. Then first we will make functional carbon. Now it is at C2. Then terminal carbon C6, CH2OH. C1 is also CH2OH. And now C3, 4 and 5 are same like glucose. That is at C3. Now OH is on left hand side. Rest at C4, C5, H and OH like this. Okay. So this is the structure of 6-carbon keto, that is fructose. So glucose and fructose are functional isomers of each other. So we are done with this first type of structural isomer, that is functional isomerism is done. Now coming to next is enantiomerism. Write down enantiomerism is also known as capital D, capital L isomerism. So enantiomerism also known as capital D, capital L isomerism. Be careful, this is not small d, small l. Small d, small l we'll be doing later, that is in optical isomerisms, right? This is capital D, capital L isomerism. Also, they are known as mirror images of each other. One trick for question solving here, that whenever in a question they write some isomers are mirror images of each other, then you're very sure it is enantiomerism or capital D, capital L isomerism, whatever is given, because no other isomers are mirror images of each other, right? Now let's see what is the definition of enantiomers. See, same as molecular formula, there's no need to mention. Now what is different? In enantiomerism, we have different H and OH orientation, different H and OH orientation around the penultimate carbon, around the penultimate carbon. Penultimate means second last carbon. Penultimate means second last carbon. This carbon is here is also known as reference carbon, right? Second last, that means at second last carbon there is different H and OH orientation. So let's see the example of D-glyceraldehyde and L-glyceraldehyde. In case of glyceraldehyde, now second last carbon is C2. So C1 and C3 will be same, right? But there is H and OH orientation different at C2, that is second last carbon, penultimate carbon. So D-glyceraldehyde, D means right hand side, L means left hand side. So at C2, when OH is on right hand side, it is D-glyceraldehyde. At C2, when OH is on left hand side, then it is L-glyceraldehyde. And now there's a mirror in the center of both these compounds. You can see that they both are isomers. They are mirror images of each other, right? Now let's see the example of D-glucose and L-glucose. In D-glucose and L-glucose, now the second last carbon is C5. So at C5, if OH is on right hand side, it is D-glucose. At C5, if OH is on left hand side, it is L-glucose. And they are mirror images of each other. They are mirror images of each other. Now note one point which is a very confusing point, that to make mirror image, we have to do alteration of H and OH at C2, C3 and C4 also. So the structure will be C2, HOH, C3 is OHH, C4 is HOH. But this all will be altered in case of L-glucose. That is C2 is OHH, C3 is HOH, C4 is OHH. So now note here that there is H and OH orientation different at C2, C3, C4 and C5 because actually enantiomerism is different H and OH orientation around all the asymmetric carbons. In case of glyceraldehyde, there was only one asymmetric carbon, that is C2, so there was no problem in understanding that structure. But now in case of glucose, there are 4 asymmetric carbons from C2 to C5. They are asymmetric carbons in glucose. Enantiomerism is different H and OH orientation around all the asymmetric carbons. Because to make mirror image, we have to alter all the asymmetric carbons HOH orientation. But then tell me, why in the definition, always in books they write that H and OH orientation different only around penultimate carbon, they write, right? Understand this concept. Sometimes it may happen that somebody will say OH is left here, so this is L. Somebody will say no, OH is right here, this is T. So like that, there can be a confusion. So we have kept one carbon as a standard, that everybody will look at second last carbon to tell which is D, which is L, right? Just to tell which is D, which is L, we have to look at second last carbon. Otherwise, H and OH orientation is different around all the carbons, right? So enantiomers are capital D and capital L. Now tell me, for carbohydrates, which form is abundant, D or L? And also they can ask you for amino acids, which form is abundant, D or L? You do this thing, no? That for carbohydrates, it is always the D form which is abundant. For amino acids, it is always the L form which is abundant. But now for solving questions, we have to see some detail. Let's see. Which form of carbohydrate is abundant? You will say D. But if they ask you which form is abundant in body, in cell, in plasma, in nature, then you will say D. Be it anything, any damn question they ask you for carbohydrates, you will say D form is abundant. But in case of amino acids, see, in case of amino acids, which form of amino acid is abundant? It is the L form of amino acid which is abundant. And if they ask you in protein, then also it is L form which is abundant. But free amino acid can be present free in the body. That free amino acid may be L, may be D. And whenever we write the name of any amino acid, we do not mention it is L or D. Say we write glycine, right? We have written glycine. We have not mentioned it is capital D or capital L. So when we have not mentioned, then it is always capital L. That means alanine written means L-alanine, right? There's no need to mention because L form is more abundant. But D form is also present in the body. When amino acid is free in the body, it is not present in the proteins. So that amino acid can be L also, can be D also. And it is very important to see the examples of D amino acid, that is D-serine and D-aspartate, they are found in brain. So if they ask you a question that which form of amino acid is present in body, and they can ask you which form of amino acid is abundant in body. When they say present in body, then both D and L forms are present. When they say abundant, then you will say L form is abundant, right? Now, few amino acids we can synthesize. The amino acid which we can synthesize in body, they are always the L form which we can synthesize. So, can I say that the source of D amino acid is always exogenous? That is, it is coming from diet, coming from outside source. The source of D amino acid is always exogenous because we cannot make D amino acids in the body, right? Okay, now coming to the third type, epimerism. Epimerism is different. Every time we have to see what thing is different. Now it is different H and OH orientation around only one carbon other than penultimate carbon. Enantiomerism was at penultimate carbon, but now epimerism is only one carbon other than penultimate carbon. Let's see the examples. See the structure of glucose. Glucose written here, mannose written here. If you compare the structure of glucose and mannose, you can see that there is H and OH orientation different around C2. And when you compare the structure of glucose and galactose, then you can see that the carbon H and OH orientation different around C4. So can I say mannose is epimer of glucose at C2 and galactose is epimer of glucose at C4? And tell me, mannose and galactose, are they epimers of each other? Mannose and galactose, they are not epimers of each other because they differ in 2 carbons, that is C2 also and C4 also. And the definition of epimerism is that different H and OH orientation around only one carbon other than penultimate carbon. Okay, so we are done with the epimerism also, and the next one we have to do is anomerism. But in anomerism, before doing with anomerism, I have to tell you a few basic points. See, linear form of carbohydrates, linear structures we have done till now. Linear structures will be converted to cyclic structures in solutions. When carbohydrates are present in powder form, then it is a linear configuration which exists. But when carbohydrates are present in this solution form, then it is a cyclic configuration which exists. So when linear structure has to be converted to cyclic structure, see my hands here. Let's say linear structure. This is a linear structure. If this linear structure has to be converted to cyclic, then some carbon from here should be combining with this carbon and making cyclic structure, right? So in this case, in case of carbohydrates, when linear is getting converted to cyclic structure, then the 2 carbons which combine are functional carbon always combined with second last carbon. In case of glucose, let's see the example. In case of glucose, the functional carbon is C1, second last carbon is C5. They will be combining to make cyclic structure. C1 is, double bond oxygen and hydrogen here. C5 is H here and OH here. So when these 2 carbons have to join, they will join with the help of oxygen in between. See here, the C1 is attached to oxygen with the help of 2 valencies. So one of the valency of C1 can be given to C5. On the other hand, C5 will give OH back to C1. Now when we individually look at C1, which 4 things it has now? It has one H here, one OH here given by C5, one valency occupied by oxygen, and here on this side there's a big group I'm just mentioning R. That is, this big group I'm just mentioning R in that place, short form of that big group. So we can see that all these 4 valencies of this carbon are now different. So this carbon is now asymmetric. This is functional carbon which was symmetric in case of linear configuration, we have seen that. But now in cyclic structures, this carbon becomes asymmetric. So because of this extra asymmetric carbon in case of cyclic structures, we have one extra isomerism which is only there for cyclic structure, and that is known as anomerism, which is the 4th type of structural isomerism. So now in anomerism, the definition will be different H and OH orientation around the functional carbon. Because functional carbon is asymmetric, so we will say different H and OH orientation around the functional carbon. Functional carbon can be C1 or C2, depending upon it is aldehyde or keto. If it is aldehyde, then it is C1. If it is keto, then it is C2, right? Now, when cyclic structures are formed, then 2 kinds of cyclic structures are formed. One is pyranose, other is furanose. Pyranose is a 6-membered ring. Furanose is a 5-membered ring. Let's see these rings here. This is pyranose ring, oxygen present here. This is furanose ring, oxygen is present here. So if I ask you how many carbons are present in pyranose ring, then the answer is 5 because 1 is oxygen. Pyranose is a 6-membered ring, but number of carbons are 5. And similarly, furanose is a 5-membered ring, but number of carbons are 4 here. Now, in case of glucose, mainly it is pyranose, 99% pyranose, but 1% furanose also exists. But in case of fructose, it is opposite, 99% furanose and 1% pyranose. So, I will say if glucose is mainly pyranose, fructose is mainly furanose, but I'm not saying only. Glucose is not only pyranose, glucose is not always pyranose. I am saying glucose is mainly pyranose, fructose is mainly furanose. And these are 6 carbon containing sugars, glucose and fructose, 6 carbon containing sugars known as hexoses. So we can say for hexoses, both pyranose and furanose exist, but for pentoses, only furanose exists. Right? Pentoses like ribose, that is having 5 carbons, that will be only furanose form which will be existing for ribose. So let's see these pyranose and furanose forms of glucose and fructose. In glucose pyranose, oxygen is here in the pyranose ring and oxygen is shared between functional and second last carbon, that is C1 and C5 here. If C1 is here, then next is C2, next is 3, next is 4 and C6 is out of the ring. This is the pyranose form of glucose. Then see the fructose furanose form, oxygen here shared between functional and second last carbon, that is now C2 in case of fructose and second last is same C5. So C3 here and C4 here. So you can see, you can look, C1 and C6 are out of the ring. And similarly, ribose is also furanose and oxygen is shared between C1 and C4 now, C1 aldehyde, C4 second last carbon, right? This is ribose. Now, anomers are of two types, alpha and beta. Alpha and beta. Let's say this is alpha glucose and this is beta glucose. So this, say C1. In glucose, this position is C1. Now at C1, if OH is downwards, it is alpha. At C1, if OH is upwards, then it is beta, right? In your guides, sometimes wrong things are given. They write opposite, OH upwards is alpha and something like that. So do not get confused. Refer to this, what I have given you, that OH downwards is alpha and OH upwards is beta, right? So we're done with structural isomerisms 4 type. Let's do the revision. Now the first one was functional. In case of functional, there is different functional group. There is different functional group. In case of enantiomerism, epimerism and enomerism, in all these three, there is different H and OH orientation around some carbons. In case of enantiomerism, it is the penultimate carbon. In case of epimerism, it is only one carbon other than penultimate carbon. And in case of enomerism, it is around the functional carbon. Now, can you distinguish between this functional carbon and this functional? See, in functional isomerism, there is different functional group. But in case of enomerism, there is different H and OH orientation around the functional carbon, right? So we're done with structural. Now the next one is optical. In optical isomerism, now again, same thing will be what? Same is molecular formula. Again, same is molecular formula, but different optical properties. Now these isomers will be having different optical properties, that is, they can rotate the plane polarized light. So let's see. Let's say this is a test tube. In this I have taken solution of a carbohydrate. This is solution of carbohydrate. From this solution, if I pass a plane polarized light, then the light will be rotated. The light will be rotated either towards right or towards left. If the light gets rotated towards right side, then the sugar present in the solution is known as dextrorotatory, represented with small d or plus sign. But if the light gets rotated towards left side, then the sugar present in the solution is known as levorotatory, represented with minus sign or small l we write. So be careful, small d, small l are optical isomers, capital D, capital L are structural isomers. Now glucose is always small d, that is glucose is always dextrorotatory and fructose is always levorotatory. And the levorotatory power of fructose is more than the dextrorotatory power of glucose. Let's say levorotatory power of fructose is minus x. I'm using minus because it is levorotatory, and glucose dextrorotatory power is plus y. That means now I'm saying x is more than y, right? Levorotatory power is of fructose is more than the dextrorotatory power of glucose. Now what is racemic mixture? Racemic mixture is equal small d and small l present. I'm writing word equal. Do not use the word both. The better word is equal here. Equal small d and small l present in a solution, that is racemic mixture. Now because it is equal, that's why racemic mixture is optically inactive. Racemic mixture is optically inactive. Now let's see what is racemase enzyme. Racemase enzyme is that enzyme which interconverts the two isomers? Small d small l or capital D capital L? You tell me. See, Reismann's enzyme is that enzyme which interconverts capital D capital L into each other, not small d small l. The name Reismann's is a misnomer. Don't go by the name. The name is misguiding you, right? So I repeat, Reismann mixture is equal small d small l, but Reismann's enzyme is that enzyme which interconverts capital D capital L into each other, right? Now let's see the number of asymmetric carbons in some important monosaccharides. So first look at glyceraldehyde and dihydroxyacetone. You know the structure of glyceraldehyde is this. There is aldehyde group at C1. This is glyceraldehyde 1, 2 and 3. I've already told you how to make the structure. And dihydroxyacetone is this. Dihydroxyacetone. They are functional isomers of each other, right? Now we have to see how many asymmetric carbons are there. First look at glyceraldehyde. In glyceraldehyde, C1 is symmetric. C1 is symmetric. This carbon is attached with oxygen with double bond O. Two valencies occupied by same atom, that is oxygen, so it is symmetric. Then C3 is also symmetric, that is CH2, two hydrogens, same, so symmetric, right? Now this C2 is asymmetric. Look at C2. For C2, one valency is by H, other valency is OH, third valency is by group CHO, fourth valency is by this group CH2OH, right? All four are different. So C2 is asymmetric. So there is one asymmetric carbon in case of glyceraldehyde. Now see DHA. This is two hydrogen symmetric, two hydrogen symmetric, double bond O symmetric. So there is no asymmetric carbon in case of DHA. So DHA is the only carbohydrate with no asymmetric carbon, right? Once this question was asked. So which is the only carbohydrate with no asymmetric carbon is DHA, dihydroxyacetone, right? So the aldehyde form of 3-carbon aldehyde form has one asymmetric carbon. 3-carbon keto form has 0 asymmetric carbon. And one general statement I will tell you here, that number of asymmetric carbons in keto form are one less than the aldehyde form, right? You can see the example here. There is one asymmetric in the aldehyde form, but there is 0 asymmetric in the keto form. So we can say that number of asymmetric carbons in keto form are one less than the aldehyde form. Now let's see how many asymmetric carbons are there in glucose. The structure of glucose: 6 carbons. First is aldehyde, last is CH2OH. On remaining carbons make H on left side, OH on right side, but at C3 OH on left and H on right. This is the structure, right? So C1 is symmetric, double bond O. C6 is having 2 hydrogens. This is also symmetric. Other 4 carbons are asymmetric carbons. let's see how. Some students have confusion, so let's see how. Look at carbon 2. When you look at carbon 2, see the 4 valencies. One is hydrogen, other is OH. Other valency, third valency is occupied by this group CHO. Fourth valency is occupied by this group having 4 carbons. So all 4 valencies are different. So C2 is asymmetric. Now look at C3. When you look at C3, then you have one valency which is occupied by OH, other valency with hydrogen, third valency with this group having 2 carbons, right? Fourth valency by this group having 3 carbons. So again, this is asymmetric, right? So the main thing is that you have to take the full group as the valency, right? Do not see like this is carbon, so here we have C, here we have C. Don't do like that, okay? Now look at C4. When you look at C4, one valency occupied by hydrogen here, other valency occupied by OH here, third valency occupied by a group having 3 carbons, fourth valency occupied by a group having 2 carbons, right? So all 4 are different. Now look at the last one, C5. When you see 4 valencies of C5, one is H, other is OH, third is CH2OH, fourth valency is occupied by a group having 4 carbons, right? So we have 4 asymmetric carbons in case of glucose. So number of isomers in case of glucose is the formula 2 to the power n. N is number of asymmetric carbons, so 2 to the power 4, and this is 16, right? Note one more point here, that when we use this formula, then we take these 4 asymmetric carbons, not 5 here. I told you in cyclic structure, one more asymmetric carbon is formed, right? But when you use this formula, then do not consider the extra asymmetric carbon of cyclic structure, right? Only take the asymmetric carbons of linear structure, so it will be 2 to the power 4 and not 5 here, right? This is it with isomerism. Thanks for watching.